and you go in the direction of the descent, you can reach the global minima. All that is great, but if that is what you want, then PUC is enough, right? So that will tell you. But how do you know that that is true in some 100 billion dimensional space, right? Or 10 million dimensional space, which is not at all impractical, right? Nowadays you have deep neural network with 10,000, 10 million, or even 10 million coefficients, right? If you have 10 million coefficients, it's 10 million dimensional space that you are looking at, right? F of x1, x2, x3, and so on, x 10 million, right? That's the dimension. So you're optimizing such a function. So now, how do you know that things won't be like this? So how do you prove this? What is the first thing that you? I mean, if you see this kind of mathematical problem, what is the logically? What is the first thing that comes to your mind? Huh? How will you prove that there cannot be more than one? Huh? Explicitly show somehow, right? You look at all possible functions and say, well, none of these have two minimas. Otherwise, proof by, okay, I have, huh? Huh? Sorry, can you repeat what? Contradiction, right? So you can prove by contradiction. So what do you mean by contradiction? You assume that there are two, right? Or multiple, but two is enough, right? If you can prove for two, you can prove for multiple. So that's what we will see. We will try to see if you can prove. Okay. Suppose you have two values, xy belonging to domain of f, or two minimas. Okay, that is f of x equal to f of y, and f of x is less than f of z for all z in the domain, or let's say all z not equal to x, z not equal to y. That means I'm taking 2 points x and y, the function values are same, and one is less than, so you take any other point, f of this is the lowest points, right? So it's fine. Okay, now how do you argue out that this cannot happen? You basically show that, see, we start with a convex function, okay, strictly convex function. You have to prove this. If it's strictly convex, what is the trick? I use a convex combination somewhere here, right? Right? I use some convex combination and show something, right? All right, is that fine? Or okay, there is another picture that I can write. This is also fine, right? Something like this. Well, not really like this. Something like this. You cannot have these kind of things also, right? This should be unique minima, right? So how do you find, what do you do? Huh? So I take convex combination of x and y, right? So then f of lambda x plus 1 minus lambda y is definitely, remember this is important, strictly less than, it's a strict convexity, lambda f of x plus 1 minus lambda f of y. You agree? But what is f of x and f of y? What is the relationship? Equal, right? Lambda f of x plus 1 minus lambda f of x is what? Of x. So this is definitely not equal to x or y if lambda is not equal to 0 or lambda not equal to 1. So I'll pick lambda equal to half, for example, okay, or not equal to 0 for it's not equal to 0 x or y if lambda is half, for example. It's x plus y by 2. X plus y by 2 can never be equal to x or y, right? So that means I'm coming up with a point, right, that is whose function value at that point is smaller than x. But what did we assume? We assume that x is the global minimizer, right? But I'm coming up with another point which is much better than, right? It's almost like saying, okay, there are two neural networks which will work really well for a convex function or loss and everything is convex. Then what I'm saying, I'm going to come up with a new neural network which is much better than both. But what is the assumption? Those two are the best neural network, right? So I'm contradicting the assumption that those two neural networks are the best. Right? There can only be one. Right? So a contradiction.